I will begin. Heavenly Father, we thank you for this day. Again, Lord, I thank you for the students, and I just pray with us today, help us to glorify you in what we do, Lord. In your name I pray. Amen. All right, so we were talking about vector fields. In fact, that's most of what we're talking about the rest of the semester. And so I guess I should probably start us out with just explaining what on earth a vector field is. I actually have talked about this before, all right? We talked about, let's see, the first vector fields we talked about, we thought about a space curve, right? And we thought about attaching a tangent, normal, and binormal vector along each point on the curve. That gave us what's called a vector field on the curve, right? That was kind of interesting. It revealed various geometric aspects of the curve. And then if you've been paying really close attention, you notice that we've been talking about vector fields in our study of the gradient of a function, right? So the gradient is actually an example of a vector field. But what is a vector field? Here's a sort of generic definition. It's an attachment, or assignment if you like, of a vector at each point in some object. Now, for the most part, this object going forward, we're either going to be talking about like R2, we might be talking about R3. We'll also talk about vector fields on a surface. All right, a surface inside R3. These are the big ones. So let's just talk about R2 for a second. What's a vector field on R2? What's it look like? So it would be f of x comma y equal to, here's typical notation, p, which is a function of x and y, q, which is a function of x and y. Now, a lot of textbooks, they wouldn't write it this way. They would instead write something like this. Well, first of all, they wouldn't write the of x, y. They just say f is equal to p. Well, here's what I would write. I would say px hat plus qy hat. The standard textbooks tend to use the ij notation, right? Like pi hat plus qj hat. But you got to understand that that vector is attached to the point x comma y, right? Typical notation for R3, we have f, which is a function possibly of x, y, and z. And so you have p of x, y, z, q of x, y, z, r of x, y, z. All right, if I drop the point notation and I just write f something like px hat plus qy hat plus rz hat, that's a vector field. We're attaching a vector at each point in space. Now let me attempt a more in-depth example. We could look at this one, f of x comma y equal to minus y comma x. All right? So this is a kind of important vector field. Let me just try to, now this way I'm doing it, this is probably the only time that I will approach it from this method and just specifically plot vector after vector point by point. But I think it's important for us to do this as we're starting. Much like when you're starting to graph functions, you make tables of values. It's kind of like that. So let's see here. We should start out with maybe a relatively simple point. How about this? What if we're at 1, 0? So I'm going to make a table over here to collect my work. So here's my point. Here's the vector. So if I plug in 0, 1, what do I get out? What's the vector I get out? I get minus 1, 0, right? And what's that? That's, oh man, uno momento. That seems wrong. It's like, geometrically, that's not what I was expecting. That's true because I made a mistake. What should I write there? So, phew, all right. It's not just us. We're not all the. I mean,
blame it on Chopin.
We were worried that Jesus had come back and that we were all left behind. That was.
So Chopin just came back.
That was Joshua's theory. He said if you miss class, it was a event with deeper meaning. Okay, so you said Chopin came. What did you say about Chopin?
I said you can blame it on Chopin.
Oh, Chopin.
I came from my piano lesson.
Oh, I figured it was piano related. All right, so yeah, so y is 0, right? So this is 0 and 1, which is a vertical vector, right? So if I picture that over here, it's something like this. All right? What happens if I plug in, oh, I'm an idiot. Oh, man, what did I just do? I am sorry, guys. I have problems. All right, so here's the problem, guys. I meant to put 1, 0 here. I'm thinking 1, 0 here, but, you know, this is why I was so confused, is I was thinking 1, 0, but I wrote 0, 1. Now, 0, 1. This point, right? Plug in 0, 1. We have x equal to 0, y equals to 1, so that's minus 1, 0, right? So that is that vector. You notice we're attaching the vector to the point in question, right? That's the way it works. So like a more obnoxious notation would be something like f of xy is really a pair. It's the point xy and the vector f. Well, it's in the vector pq, you know? There's a base point and there's a vector. They're both involved in the vector field. But anyway, we don't typically use that notation, so I probably should cross this out. Okay, so next point, how about minus 1, 0? What's that give us? Zero minus 1, all right. So that's like over here. And then finally, how about 0 minus 1? That'd be down here somewhere. What's that give us? It gives us 1, 0, which is like so. All right. And the thing is, if you plug in more points, right? What happens if you plug in like the halfway points? Right? Something like that. If you plug in the, you know, if you're out here at length 2, they're like this, right? And if you were to look at points other than the coordinate axes, you'd have, you know, tilted, right? So how should we visualize a vector field? I mean, one way would be to just pick a grid of points and evaluate the vector field at that grid of points and just draw the vectors, right? But if we do that and we actually illustrate the magnitude of the vectors as they are, you see the picture gets really cluttered really fast, right? So one of the things people do visualizing vector fields is they're not honest about the magnitude as it scales to the picture. Like instead of actually drawing them the length that's proportional, we'll just draw like a standard length vector and just really just try to illustrate the directionality of the vector field rather than the magnitude with our picture of a vector field. That's one thing that you can do. The other thing with Mathematica has something called stream plot or streamline plot, I forget, something like that. And what it does is it doesn't plot the vector field directly, it plots what are called integral curves to the vector fields. What's an integral curve to the vector field? Integral curve aka a flow line, to F, is a path for which we have the following. We have F of R of t is equal to dr dt. What this means is that the given vector field along the curve reproduces the tangent vector field to the curve. With this equation means that the integral curve lines up with the vector field, wherever it is, right? And the reason I say flow line is if the vector field has the specific meaning of like the velocity of a liquid, right? If you were to, drop a little dot of dye into the liquid and watch where it went, well, that dot of dye would trace out the flow line in the liquid, right? That flow line is an integral curve to the velocity vector field of the liquid. So an interesting mathematical problem is to find the flow lines of my given vector field here. What would that mean? What does this actually look like? This is kind of an abstract condition. What does this actually mean for my example? This would mean that we had minus y comma x equal to dx dt, dy dt, where I'm just using r equal to x comma y as my notation for the path. So you see we have to solve differential equations in this case. We have to solve dx dt equals to minus y, and we have to solve dy dt equals to x. Which is kind of a drag because, well, the pesky thing about Calculus 3 is it comes before differential equations. Right? So you guys don't know how to solve this. And you're not supposed to know how until about a half a semester forward. And even there it's questionable depending on what Wang does in a given semester and me the same. I mean, I may or may not get to this, depending on the crowd. But no, that's not true. I always get this. But how do you solve these? I'm just going to tell you the solution. The solution is x equals to r cosine t plus some phase angle. Then what's y equal to? R sine t plus some phase angle. In differential equations, you can derive this. Actually, you could use the technique you guys learned in Calculus 2 to do this, right? You may or may not have covered this in Calculus 2, but one way you could solve this would be just to eliminate t at the level of calculus. So you could look at dx dt over dy dt, which would be dy dx, since this is an autonomous system. And dy over dx would be what? It would be x over minus y in this case. So this gives us minus y dy equals to x dx. And in fact, you can solve that using Calculus 2 techniques. That gives us the solution x squared plus y squared equals to r squared. But solving these is better because it actually keeps track of the direction of the vector field. Right? This is an oriented curve. As time increases, it goes counterclockwise, which I think is what we want here. Yeah. This is counterclockwise, right? Whereas if you do this trick over here that you might have learned in Calculus 2, you lose all sense of direction. You just get the level curve, but you don't get a sense of what the direction is for the integral curve, which might be all you want, I don't know. So long story short, I can go back to my picture and I can draw the integral curves, right? The integral curves here are circles, right? And so this is the other way we can visualize vector fields. We can draw streamlines, integral curves to the vector field, and that will tell us what the vector field looks like. This is especially important in Physics 232, where we look at field lines to describe electric and magnetic fields, right? For example, so here's the two most important examples from physics. The electric field is kq over r squared, r hat. And what that means is this r hat is really, okay, in our language, here's our language. This is kq over rho squared, rho hat. That's actually what our notation is this semester for that. And so what that is, if I look at the origin, there's just field lines coming out every different which way. And I can't really do this justice, but these should be symmetric from the origin, coming out at you, going into the board, going every different which way, symmetrically so in all directions. These are the field lines. And so we think of electrostatics, we think of the field lines as emitting or emerging from where the charge is. All right? So these lines I'm drawing for you, these are the integral curves. These are the integral curves of the electric field. And this is also known as the spherically radial field. The magnitude obeys the inverse square law, right? So that's one example. Another example is the magnetic field, which is mu naught I over 2 pi r theta hat. This is the magnetic field from a steady current flowing along a wire, which I'm envisioning in the z-axis. The magnetic field wraps around that wire just like theta hat does for us. So if we have, I will foolishly attempt a picture. So suppose the current is going up like this. The magnetic field encircles that by the right-hand rule. You can envision the field, the flow lines like this. So I have better success drawing it. So suppose the current's coming out of the board, right? The magnetic field line looks like that. So when you draw magnetic field lines, what that's saying is that if you pick a point, right, then the direction of the magnetic field is tangent to the curve of the field line, like that. So this is the convention we use in physics to visualize vector fields. Because drawing an array of vector fields, and drawing an array of vectors by hand is just impossible, right? But you guys can sketch field lines, right? For example, a dipole. If you have a negative charge here, you have a positive charge here, you can easily sketch field lines. They go from the positive to the negative. Right? I can easily sketch those field lines, and you pick any point in space. If I did it right, I got to tell you the direction. They all flow out of the positive charge and they flow into the negative charge. That's the conventions in physics. So if I pick a point here, I can tell you that the electric field from this dipole distribution points something like that. My point to you is if we use field lines, the integral curves to the vector field, it allows us to visualize a whole bunch of vectors at once without actually drawing all of those vectors. I think it's important to talk to you guys about this early on because I won't talk about it too much in here, but it's actually really, really important as you apply this class to physics, okay? So we have electric fields, we have magnetic fields. Another example is the following. If we have a force n is equal to minus the gradient of u, then it's said to be a conservative force. Or force field, really, if you like. And here u is the potential energy function, right? So that's it could be gravity, it could be springs, it could be combinations of those sorts of things. We'll talk about that in more depth as we develop the vector calculus. All right, so there's a crash course in visualization. There's only so far I can go without using technology in here in terms of visualization, and it would be a shame to not show you at least some picture with the grid of vectors, which I can't do justice drawing by hand, right? So I haven't had a chance to sit and investigate what's out there in terms of plotters. So there was this thing that happened with the security in Java that destroyed many of my websites that I cared about. I don't know. But here's one. It's linked to my home page. So guys, in my in my homepage. I have links to websites that do the math for you. The one we're looking at right now is actually 16. Well, it might be 18. I think it's 18. Yeah, it's 18. Ooh, look, it comes with a surface built in. Whee! See if I can make it. Ha! Whoa! Look at that. Fancy pants. It's here. Let me go that way. So you can do things like, for example, add vector fields. So what I did here was something kind of funny. You can also add sliders, which makes it more fun. So because this I could not draw for sure. And so let me try to explain what's going on here. Let me stop with this nonsense. So down here is the vector field, which I've just made BBB. And so like if B is, say B is 1. B is 1. All right, so what we're looking at then is the vector field 1, 1, 1. And this is just, if you go down here further, you can see that I've chose to illustrate it for 3 z values. That's just the nature of the website, okay? And so you can see that this is the vector 1, 1, 1. Let's see here. Let me try a different one. Or you could look at x, y, z, right? What would this thing look like? Does that make sense? See if I can keep it like that for a second. So the xyz vector field, it's 0 at the origin, right? And then it actually points radially outward, if you can envision it. This xyz vector field, I personally love our notation, xyz. How could we rewrite that? We could rewrite that as, rho hat. That's the vector field that points outward in the spherical direction, proportionate to the distance from the origin, actually. If I was to say, let's see here, what if I put the one we were just looking at, minus y, x, right? And I'll keep it horizontal. See, that's the one we were just looking at. You can see it wraps around the z-axis like that, right? Or you could do stuff like, I don't know. What should that change? I don't know what that'll look like, actually. Ooh, look at that. What would the integral curves to this thing be? You can kind of see it, right? They'd be something that integral curve would go like this here, then it would go like that. It's hard to see those. It'd go like this over here. It'd be going like this. They're hyperbolas, right? Okay, so I hope I've given you some indication what a vector field is, right? Why it's important. It's important to physics because it describes electric fields, magnetic fields, force fields, and mechanics, all vector fields. But there's more. You can talk about the velocity vector field to a liquid, right? The integral curves there will be like streamlines. This is something you'd look at if you were, say, designing a car and trying to reduce drag, right? You look at streamlines of the velocity field. And so understanding the calculus of vector fields is important because it has to do with fluid flow and electricity and magnetism and pretty much any interesting part of physics these days in some way or another involves vector fields. Then there's those vectors biologists talk about. I don't know about those. So you don't ask me about that. The attack, what's an attack vector?
The means by which intruders or hackers gain access to a system.
Some sort of cyber hackery. Talking about hacking or something. All right, well, so this idea that the vector fields can be drawn with, you can use streamlines to draw vector fields. It doesn't make sense for all vector fields, actually. There's something very special about the vector fields which are studied in physics which allows this visualization in terms of lines like this to make sense. There's more here that I've not explained yet. In physics also, the density of lines illustrates the magnitude. So you can see that the electric field is stronger near the origin because the lines are more densely packed. For a given surface that you go through, the number of lines which go through a given surface area is much smaller as you go out, right? So the number of lines piercing a given surface area, that has to do with the magnitude of the field in physics. So the number of field lines piercing a certain surface is an important idea. That's what's known as flux. Flux is the number of field lines that cut through a surface at a given area. Now, and likewise here, well, it's harder for me to explain there, but again, as the lines get more spread out, the magnitude is weaker. Where they're most densely packed, the magnitude is largest. If you ask what the magnitude of the electric field is at the charge, then you'll be in trouble because we can't say. It's not defined. If you look at the formula that I wrote there, which is the so-called Coulomb field, what happens when rho equals to 0? It would be undefined, right? And yet that's a really important and physically relevant point. That's where the charge is. Yeah? So the infinity is not something that can be ignored. It's something that has to be focused on and understood ultimately. That's one of the deeper problems in here, is grappling with that issue. All right. Now I'm about to show you something that's more mechanical. So this, I think, what I'm about to show you, you guys will be able to do. But doing it and understanding it are two very different things. So I'm just going to show you how to do. I'm not going to teach you how to interpret today. So the two things I want to teach you how to do now are how to calculate divergence and the so-called curl of a vector field. All right? So first of all, the definition. Divergence. So we write nabla dot f, and that is equal to partial p, partial x plus partial q, partial y plus partial r, partial z. This is the divergence of the vector field P, Q, R. All right? The curl, we write nabla cross F, and that's itself a vector again. So what this is partial, I got to think for a second here, guys. Partial R, partial Y, minus partial Q, partial Z. Partial P, partial Z, minus partial R, partial X. And let's see here. Partial XQ, partial Q, partial X rather, minus partial P, partial Y. This is the so-called curl, sometimes called the rotation. All right. Now, there's a mnemonic here. You could remember it by this heretical mathematical formula, x hat, y hat, z hat. You got your partial x, you got your partial y, you got your partial z, and you feed it p, q, r. That determinant pattern still gives you that thing with the proper interpretation, right? You see how that is? If you look at it, we got like x hat times partial yr minus partial zq, right? Minus y hat partial xr minus partial zp plus z hat. I'm partly writing this down to check my work. partial y, sorry, z hat, partial x rather, q minus partial yp, yeah? Is that what I had up? Does that match? This should be that. Yep. This should be that. accounting for that minus, right? Yeah. And this one should be that one. Right. So there's something, so that, you know, the larger discussion here is that we have divergence, we have curl. There's something else we've already done though, right? What's the thing we've already done? Remember? Nabla F is what? So keeping it 3D here for the moment, this is also the gradient of F. So in some sense, this operator, right, this nabla, we can think of as being x hat partial partial x plus y hat partial partial z, partial y rather, plus z hat partial partial z. This is a vector of operators. Is apparently somewhat important for our discussion. Yeah. You got to be careful, but you can kind of understand these definitions just in terms of some sort of formal dot product or formal cross product, right? So one of our larger goals as we go on is to understand what on earth these quantities mean for a given vector field, right? So let's work them out. Let's look at, here's the simplest one I can think of. Oh, here would be, actually this is even simpler than what it was. How about if you look at the vector field 1, 2, 3? This is a kind of stupid vector field. What's the divergence, what's the curl of this? 0 what though? 0 the number or function, right? Depending if you want to think about the point being fixed or varying. But anyway, it's a scalar. Right? The curl, on the other hand, is what? It's the 0 vector. That's the most important distinction between, like basic distinction between divergence and curl. Divergence is a scalar function. Curl is a vector. All right? This example is too stupid, though, because all the derivatives are 0, right? I don't think it gives us much insight at all. How about, what if we do my nice vector? What if we do the XYZ vector field, this one? What's the divergence of this vector field? Yeah, the divergence is 3. And it's 3 no matter where you are, right? It's 3 in all of space. Interesting. What's the curl of F? So we're looking at, well, I mean, I'm going to use the mnemonic if you guys don't mind, because it's easiest to kind of see what's going on here. Yeah, it's just 0 because as you sort through this formula, you know, you got partial y acting on z, you got partial z acting on y, you got x acting on z, you got z acting on x, you got, you know, x on y and y. I mean, everything, it's always what you don't need to get something non-zero, right? All the partial derivatives here are 0. So the curl of this vector field, the curl of the, you know, radial vector field is 0. What if we look at the 3-dimensional extension of the one I did today, minus y, x, 0? So that would be doing the one with the circles, but the same at each z. So it's kind of, yeah. What's the divergence of this? So I heard a 0. What's the curl of F? let's see here. So we've got, I'm going to write out this thing again, because I think this might be actually a good way for you guys to try to keep on the straight and narrow in terms of the calculation. Maybe. I mean, curl is, in some sense, like the cross product, right? It's got a lot of moving parts. You got to be careful. It's easy to get a sign wrong. And now we've got differentiation coming into play, right? But you can do it. This is way, way easier than any question I just asked you, right? Right? I mean, setting up any integral, no matter how easy it is to visualize, still is way more work than this, right? So what do we got? Minus 1. I get 0 for the first component. I get 0 for the second component. I get 1 for the third component. 2? Oh, yeah. Thank you. Much appreciated. Maybe that gives us some kind of hint, right, about the curl, maybe, because that vector field did what? It kind of encircled the z. If you look at it, I don't know. I can't quite put I don't know how to explain what that curl is geometrically just yet. Yeah. So, guys, are there any, these examples that we've looked at so far really quite special. Let's just look at kind of any old vector field, and I'm going to let you guys make up the formula for it this time, all right? So we have something a little bit more substantial. So what do you want the x component to be? X squared plus xy, I'll allow it. And then this looks like a y squared and sine z, sine of z. All right. I think that's sufficiently complicated. It should illustrate my purposes here. So what's the divergence of f? So we have to take the partial derivative of the first component plus the partial derivative with respect to y of the second component, and then add the partial derivative with respect to z of the third component. What's that give us? That gives us, looks like a 2x plus y plus 2y plus cosine z. So there you go. That's the divergence. Interesting. How about the curl? So I've got partial y of sine z minus partial z of y squared, comma, partial z of x squared plus xy minus partial x of y squared, partial x of y squared minus partial y of x squared plus xy. The reason I can do that, guys, is I think about the curl in my head in terms of this pattern, you know? Well, remember this? That's how I write those formulas down like I just did. I'm always thinking about this in my head. That x hat cross y hat gives me z hat. That z hat cross x hat gives me y hat. That y hat cross z hat gives me x hat. These patterns is what allows me to write those formulas down. Yeah. But anyway, it is the definition. What does it work out to? 0, 0, and then what? Whoop. minus x? All right. So it looks like if we look at this carefully, we can see that this vector field has two pieces in it, doesn't it? There's kind of like two different things going on here. Look at this. This is the sum of one vector field, x squared, y squared, sine z, that thing, right? And then the other thing that's the weirdo, well, in my view, it's a weirdo, xy, 0, 0. Right? So I could call this thing, say, A, call this thing B. I would point out to you that the curl of B is equal to 0, 0 minus x, right? And the curl of A is, in fact, 0. I can say more. A is, in fact, kind of a special kind of vector field. A, I think, if you guys search your heart, you can see that it's the gradient of some special function, let's say f. So suppose I want to say A is partial f partial x, partial f partial y, partial f partial z. Can you tell me the little f that will give me x squared y squared sine z? We had some homework problems that were kind of scratching this itch earlier without any good reason. We've got, yeah, I heard an x cubed over 3, y cubed over 3, minus cosine z, right? Plus a constant if you like. Any function like that will serve as a potential function for A. This means that the vector A, all right, so let me write it down here again. So we've got A was, what was it, x squared, y squared sine z, right? That's the gradient of the function x cubed over 3 plus y cubed over 3 minus cosine z. I'll set the constant to 0 for the sake of discussion. So this right here, this shows A is what we say conservative. A is a conservative vector field. We can write it as the gradient of a function. This is one of the questions that we're going to be asking going forward is, when is a vector field conservative? How do we detect that? How can we be sure something's not conservative, right? How do you, I mean, I can ask the question, how do you answer it? I mean, maybe the answer is right here. Part of the answer, anyway. If a vector field is conservative, let me propose that the curl of that vector field should be 0. Can we prove it? So here's my claim. If we have A is the gradient of some function f, then the curl of A is equal to 0. Let's work it out. So here's the proof. So we're given that A is the gradient of f. What's that mean? It has this very specific form, right? It's partial xf, partial yf, partial zf. That's what a gradient looks like. What happens when you calculate the curl of that? What's the curl of the gradient? So what's that? What do we got here? We've got partial y partial zf minus partial z partial yf. Then for y, I've got partial z partial xf minus partial x partial zf. And then for the z component, I've got partial x on partial yf minus partial y partial xf. But what do we know about partial derivatives? Can you guys see it? I can't tell. Okay.
Partial I and partial x equal partial x partial y.
Right.
And that equals 0.
Yeah, those partial derivatives cancel out because partial derivatives commute. I am assuming, of course, that this function is nice enough to take second partial derivatives of. So let's, for the sake of not getting into mathematical, yes, pathology is a good word. Let's assume that this function is smooth, right? And so this is 0. So there you go. And by the way, we just got a fun fact on the way, right? What's the fun fact we just learned? The curl of a gradient is straight up 0. If you take the curl of a gradient, you get 0. So what does it say? This says if we're given a vector field, we can calculate the curl of it. If the curl is non-zero, guess what? It's not a conservative vector field. For example, this right here, see this? This says then logically that there does not exist, let's say, g such that b is equal to the gradient of g. Right? We cannot find a function where b would be the gradient of g. b is not conservative because it has a non-zero curl. Does that make sense? Now, you guys might want to reverse this. So then you might say, wait a minute, so do you mean to tell me if the curl is 0, then the vector field is necessarily conservative? The answer is sometimes. And the ultimate resolution to that rests on something called Green's theorem. All right. Or Stokes' theorem, depending on our context. So, the questions I've asked today I have not really answered. I've just given you some examples and introduced some terms. The next thing we'll be doing substantively is studying line integrals, which are not really line integrals. They're integrals along a curve of a vector field. That will give us a careful definition of the work done by a variable force over a variable path, which is pretty interesting. We'll do things like we'll prove the work energy theorem, right? Past that, we'll start studying surface integrals. Surface integrals are all about flux, which is the number of field lines piercing a surface per unit area. And that will then lead us to the study of the Green, Stokes, and divergence theorem, which is actually pretty much the end of the course. So the end is near. So guys, I have found some pretty cool videos that illustrate what curl is in terms of like little discs on a river and stuff. So I think it's worth you guys watching. So I'm just gonna have, Monday is just a video day. So I'm gonna give you links to a couple videos. I think if you watch those, maybe it'll help you going forward just to gain a little bit more just visual intuition of what on earth curl means. And I won't be around Monday. Something came up, I can't be here Monday. So, but I will give you guys something to do in that. So I'll see you Tuesday. All right. Oh, your test. You want your test back, yeah? Yeah. Well, debatable.